Hello, my name is Austin Thrash, and today I'm presenting insights from my project on stroke predictions made for DA6813 data analytics applications. Strokes, as sudden occurrences that can lead to death or disability due to the interruption of blood flow to the brain, present a critical public health challenge. There are two types of strokes: ischemic, resulting from blockage, and hemorrhagic, resulting from a rupture. Common risk factors include high blood pressure, high cholesterol, smoking, and obesity. Our goal is to leverage data science to predict strokes more effectively and improve outcomes using preventative measures. Strokes are not just medical emergencies, they are also a leading cause of long term disability globally, affecting over 15 million people each year. The high incidence and impact underscore the necessity for reliable prediction models that can guide preventative measures and timely interventions. Predicting strokes is crucial due to their significant contribution to global mortality and healthcare burdens. By developing advanced models, we can identify high-risk individuals early, enabling preemptive interventions that can save lives and reduce long-term healthcare costs. To prepare our data, we started with over 5,000 records, focusing on 11 clinical features. Handling missing values, like replacing BMI's NAs to the BMI median value, and addressing the imbalance of the response using undersampling were critical steps to ensure the integrity and accuracy of the predictive models. Further data preparation involved transforming categorical variables and standardizing numerical features to ensure they were model ready. Such data handling is foundational for the effectiveness of our predictive modeling. Now let's take a look at the attribute information. Here are the features and what they represent. We have ID, which has been dropped from the dataset, gender, hypertension, heart disease, ever married, work type, residence type, average glucose level, BMI, smoking status, and the response variable, stroke. Looking at our response variable, we can see a large imbalance in the data. We're going to be using undersampling to address this issue as other sampling methods prove to be not as accurate. As we continue our data exploration, we can look at the distribution of all the features within the dataset. We can take this a step further and look at the distribution of features and how they relate to the response variable. This can be seen using a graph showcasing the age distribution of stroke patients. It might suggest that as you get older, you're more likely to have a stroke. Furthering our data exploration, we have stroke incidence and hypertension and heart disease. We can also showcase some lifestyle patterns, such as smoking status and stroke incidence. The same can also be done by looking at the distribution for BMI and average glucose level in stroke patients. And finally, we can display some general demographics relating to stroke incidence. From our data exploration, we can see that visualization of age distribution revealed that the risk of stroke increases significantly with age. Other key factors relating to strokes might include BMI, average glucose level, and smoking status. In the modeling phase, I employed various techniques, including logistic regression and machine learning methods like random forest and gradient boosting, to handle the complexity of stroke prediction. The four types of models that we are going to be implementing are logistic regression, random forest, gradient boosting, and support vector machine. The data was split into training and test sets, and cross-validation was implemented to see if it gave better accuracy. I evaluated the models using metrics such as accuracy, recall, and ROC curves. These evaluations and optimization techniques, like feature importance and parameter tuning, help us understand the trade-offs and optimize our models for the best possible predictive performance. Now let's move on to our modeling results, starting with variable importance for logistic regression. Here we can see that the most important features in logistic regression are age, hypertension, work type, and ever married. We can see that age and hypertension are also important features when it comes to random forest. Ever married appears in this list as well. And finally, gradient boosting's important variables are very similar to random forest model. Since age, hypertension, average glucose level, and BMI were important features in most models, we can assume that these features have a strong relationship with stroke occurrence. Now let's move on to our metrics. Here we have the ROC curves for each logistic regression model that I made. One baseline with all the features, one with just the top features, and another with top features and cross-validation. This process was done for most of the models. We can see that both the baseline and the top feature model perform about the same, achieving an ROC score of 84%. The random forest model performed a bit worse in terms of ROC. The best model, the one using top features, obtained an ROC score of 80%. Gradient boosting models perform slightly better than random forest, with its top features model achieving an ROC score of 81%. And lastly, we can see that the baseline SVM model performed 1% better in terms of ROC score when compared to the best gradient boosting model. Here is a comprehensive graph of all the models compared to each other. The accuracy didn't seem to fluctuate much between or within model types. I thought it was interesting that the cross-validated models were not performing better than the baseline models. This may be due to overfitting though. Again, another comprehensive graph of all my models, this time comparing ROC scores. We can see that there's not much fluctuation here either, with logistic regression achieving the best ROC score. Here's the precision for both classes on each model. The darker color is class 1, or stroke, while the lighter is class 0, no stroke. We can see that class 1 has significantly smaller values, indicating that the model may have a high false positive rate. However, since the dataset is significantly imbalanced and we performed undersampling, it makes sense that we weren't able to achieve better precision in F1 scores. Here is recall for both classes for each model. We can see that there isn't much fluctuation and that logistic regression performs the best. And our final metric is our F1 scores between both classes. We can see here, like before with precision, that class 1 is lower than class 2, except in the case of our cross-validated models. The analysis highlighted key predictors such as age, hypertension, and BMI. Models like logistic regression and random forest performed well, with gradient boosting showing exceptional ability in handling the imbalanced data. In conclusion, my project not only advanced my understanding of stroke risk factors, but also demonstrated the potential of data-driven models in healthcare. We uncovered critical predictors such as age, hypertension, smoking status, and BMI. Moving forward, further tuning of the parameters and refining of the models could provide even more precise predictions, paving the way for real-time stroke risk assessment in clinical settings.